Hello and welcome to Zero to Pong. In this video, I'll be showing you how to go from a fresh Windows install to a functional, if simplistic, game of Pong. This video is hopefully going to be the first in a series that I'm calling Bevy 0.14, where I plan to redo my Bevy Basics series to bring them up to date with the latest version of Bevy. This whole series will be planned out and kept in a document that I'm going to refer to as the Vault. This is an Obsidian vault that will hopefully grow and expand with this series to make a web of interconnected concepts and ideas that will represent all the knowledge that I have presented in this series on Bevy 0.14. So why am I starting from a fresh install? Well, that's pretty simple. I bricked my computer the other day, and the only way to fix it was to reinstall Windows. But this leaves us the question, why make a video starting from a fresh Windows install? And not just reinstall everything and start from there? This comes down to one thing that I've noticed with a lot of tutorial videos is that they just have an assumption that there's like a sort of a minimum amount of knowledge that you have before the tutorial starts. I've decided that I'm going to push that starting point just a slight further back so that it can start with people that have never written Rust code and may never have used an IDE before. So I'm going to go through what you need to install and then how to make a Rust app and install Bevy and all the steps required to get to the final finished game in the order that you would need to do it without necessarily understanding, but not having any steps where I skip ahead and you go, how did you get this done? And hopefully in future episodes of this series, it'll branch out and expand on the topics that I touch in this video without necessarily explaining them. Things like components and entities. So let's get started with what you need to install. First, you'll need to install Rust. This is done by going to the Rust-Lang website and installing Rust for your respective operating system. After installing Rust and its requirements that are automatically installed when selecting the quick install, you will now need to download and install Visual Studio Code. There is also a link to this in the description. This can be done while Rust is installing in the background. Once Visual Studio Code is finished being downloaded and installed, when you open it up, it should come up to the welcome screen where you can select your theme. I'm using Dark Modern because it looks nice and doesn't blind me when I open it. Next, we're going to be installing some extensions. So if you come over to this 3 blocks here with a 4th block being removed, this is the extensions tab. The extensions we want is Rust Analyzer, Rust Syntax, Crates, Bevy Snips. Let's try this one. Even better, TOML and Error Lens. Error Lens is less essential, but it's something I like to use when doing videos since it means that the error message will appear along the line next to where the error occurred instead of just being a blank line, which can make it easier to come across in video. Once we have all our extensions installed and ready to go, we can come over to the top and go Terminal. You may want to point Visual Studio Code at the particular file or folder that you would like to create your Rust projects in. For me, I've made a folder called 0 to Pong. I'm then going to go cargo init to initialize a Rust project inside this file. You can also call cargo new and then provide a name of the crate that or the project you're naming, and it'll make a subfolder instead of initializing it in a blank empty folder. But this is personal preference. I tend to make the folder first because I'm making YouTube videos. Next, we're going to go to our cargo.toml. I'm just going to make my text a little bit bigger. And we're going to say Bevy equals 0.14. This specifies to our project that we're using Bevy and the version is 0.14. Next, we'll come along to our main file. And at the top, we're going to say use Bevy prelude. Our snippets already has one made. But basically all this does is say that we want to use the Bevy crate, its prelude module, and then the star imports all of the components in prelude. The prelude in Bevy is a module that contains and publicly exports all the commonly used components in Bevy, such as the application, vectors, and different things like the default bundles, things that you will use on a common basis, basically. Anything that they think you'll use without wanting to have to directly import is included in the prelude. So when we star import the prelude, we get all these things immediately. Next, we're going to create our application. There's no need to assign this to a variable. I just like to because it means that I can do things like have dependencies and plugins that are only added like in debug mode, and you can't do that if you chain the whole thing. After we've created our app, we're going to say app.run. This will cause Bevy to actually execute our application and cause the game loop to start. Before the game loop will actually do anything, we're going to go app.addPlugins default plugins. The default plugins is a collection of plugins that Bevy has put together that is required to get a game to start. It includes things like a plugin to open the window and maintain the camera, as well as plugins for user input and a lot of other things that the default that like a game will need by default. It also initializes your 60 frame per second loop, such as, and there's all sorts of things in here. So you can see like the time plugin, the frame rate counting plugin, and these are all things that Bevy expects you to need in an application. In order to have anything appear inside our window, we'll need a camera. So what we're going to do is we're going to create a standard Rust function called spawn camera. This function will take in a mutable commands struct as its input parameter and will return nothing. This in Bevy is what you call a system. A system is any function in Rust that has a restriction on the types of input parameters it can take and doesn't have a return type. With this, we can now use the commands to spawn a camera bundle, camera 2D bundle with default parameters. This will cause Bevy at the end of the frame to instantiate an entity that will spawn the camera bundle. Now, at the moment, we're not doing anything with this function in order for Bevy to know that it needs to run it. So what we're going to do is we're going to go back up to our app. We're going to say app.add system. We then need to specify where in our application this system will run. So this one, we only want to run once at the start of our application. So we'll put it in the startup schedule. This runs once at the beginning of the game. There are two additional startup settings, pre-startup and post-startup, that can be used in order to put things that need to be initialized first before the startup functions or after the startup functions, respectively. We then pass in our spawn camera function. This will cause Bevy to spawn in a camera, but the camera will do nothing but render a gray screen at the moment. So what we need to do is create our player, well, technically our players, which are the Pong paddles. So to do this, we're going to make a component. There should be a snip for this. Okay, so using the snippets, we can construct a component. This is any struct or enum that derives the component trait. And components are basically just data that is attached to an object in our world that we can then use to distinguish it from other objects. So in this case, we're going to say that this is a paddle, and we're going to give it an up, a move up, which is going to be a key code, and a move down, which is also a key code. Key codes in Bevy are the physical location of a keyboard. This is a relatively new change, as it used to represent the actual symbol on the keyboard, as in a key code Q would be the Q key no matter what keyboard layout you have, but they've since changed this to a standardized where it would be on an American keyboard, because this was causing confusion for people setting a key who would then not work for someone on a keyboard that had been mapped differently. So now key codes represent the physical location of the key on the keyboard. So with our paddle, we are providing a key that they press to move up and a key that they press to move down. Now, this, very much like the camera, is not currently being used, and so we need to implement a system to spawn our two-player paddles. Spawn players. So this function, again, takes in our commands struct. We then say commands.spawn. In this case, we're going to use an image bundle, which represents a UI element that is an image. With this bundle, we need to provide all of the components that will be attached to the image. So in this case, we only need to specify a few of these. One being the transform, which is the physical location. So we're going to derive this from its translation using a vec3. We will say that the object has an x, player 1 has an x offset of 300, a y offset of 0, and a z offset of 0. This would put the player in the middle of the screen, 300 pixels to the left, height-wise, and on layer 0. You can use the z-axis to layer objects in Bevy. Okay. We're going to specify the background color. In this particular case, we're going to set the background color as white. This will mean that our paddles will appear as white rectangles since we've set the background color of the node. Next, we're going to specify the size. To do this, we use the style and then specify the size. We then give a width of the value pixels 10 and a height 150, I guess, I don't know. This will allow Bevy to render the UI objects into the world. We'll then derive default for the rest of the objects, and then the same for the rest of our bundle, since no other data needs to be provided, except we now need to wrap the whole thing inside parentheses, and then a comma, paddle, and specify the keys we want this player to be controlled by. So this is going to be key code key W, but this is player 1, so they're going to use their S and W keys to move up and down. The reason we wrap this in parentheses with a comma is we're making what Rust calls a tuple, and Bevy uses tuples to allow us to combine multiple components together into a greater bundle without needing to derive bundle ourselves and implement all of the code to do so. Next, we're going to repeat the whole thing again, but this time we're going to place it at positive 300, and we're going to change the key to up, the arrow up and the arrow down key. This will be player 2, controlled with the arrow keys rather than with the WASD keys. Outside of this, the rest of the parameters are kept the same. As always, when we create a new system, we need to include it in our game. Since this system is also only run once at the beginning of the game, we can include it in the same startup schedule as our previous one. We could add a separate call to add systems to do this, or like with components, we can wrap it in a tuple in order to insert them both at the same time. We can now run our code and see what comes to screen. Okay, so using image bundles isn't the best idea. Instead, we're going to swap to a sprite bundle. A sprite bundle is much more what you would expect from a game where the objects are represented as sprites rather than what you'd expect from like a website where they use a flexbox style. This does have some limitations in what parameters we can provide, but will be easier for moving things in an intuitive manner when we control things. So we're going to swap both of these out for sprite bundles. We'll comment this out to get the ID to help us. It needs a, not spatial bundle, sprite bundle. Sprite bundle. We then need to provide a sprite, which we can provide a color and a custom size. So we've provided the same information here as we did with the previous image bundle, but instead we're using a sprite bundle, which has a different set of components that it needs. Because of how Bevy is constructed, there is actually no difference between a sprite or an image except for the components attached to them. Some components that are duplicated can be shared between them if you wanted to have both functionalities. Now when we run our code, we'll see what happens. As you can see, we now have spawned 2 Pong paddles in the middle of our screen, though if I press the corresponding key to move them up and down, it doesn't do anything. This is because we haven't put a system in that moves these paddles. We'll just do one more quick thing when we come to spawning the player before we move on to making the player be able to move. And that's just, we're going to spawn a different colored background in order to make it possible to see where our playing field is without necessarily needing to go into the complexity of grabbing the screen size. Though this is possible, and I will hopefully do a video expanding on the idea of collecting the user's screen size and correcting the game's logic based on the size of the screen. The code you see here will spawn a black rectangle in the middle of the screen with a width of 700 and a height of 500. This will be our play area. The rest of the code will reference the fact that it's 700 wide by 500 tall. This should mean that our 300 offset for our paddles mean that they are inside the play area, as well as allowing the 500 to mean that they are still on the play field. I will run and compile the code to make sure that my assumptions is correct. This is very important with Rust, is to always be compiling and checking that what you think you're doing is actually what you're doing. As you can see, black rectangle that encases our play area. Next, we are going to move on to making the players able to move. To do this, we'll create a function called move paddle. This is where we're going to learn a new concept of Rust. This is queries. Queries are a way of extracting information from the game world to be able to interact and change it based on what our game is currently doing. To do this, we are going to use the query struct. So we are going to query for the paddles. So we make the variable paddles, and then we create a query. The query takes in 2 parameters, but only one needs to be provided. The first parameter is what we are actually querying for, the information we will have access to. In this case, this is going to be a mutable reference to the transform of our paddle, and also a non-mutable reference to the paddle's data. This will allow us to determine which player we are currently looking at. There is also a possibility to add filters, such as I could say with paddle. This would allow me to filter out anything that had a transform that also has a paddle without necessarily requesting the data from a paddle. This allows Bevy to run much more concurrently, but isn't important for what we're doing right now since we need to access the paddle anyway. So this implicitly gives us the filter. The filters are less restrictive ways of gaining access that allows Bevy to be more parallel than requesting the data itself. Next, we'll also need to collect the player's input. To do this, we're going to have an input field, which is going to get a resource, which is shared across the Bevy world and have only a single instance included, which allow for things that are not unique to specific items or objects in the world to be shared, such as, in this case, the inputs pressed into the keyboard. They are accessed by using the res wrapper and then including the type that you want. In this case, we want a button input that reads buttons that are key codes. Bevy does this so that we can collect button inputs from things like controllers and have them treated separately than keyboard inputs. Part of the default plugins is a system that goes through and automatically updates the input resource with the keyboard keys being pressed this frame. So next, we are going to iterate through all the paddles. This is done by calling a for loop on a mutable reference to our paddle's input parameter. You can also call .iterMute, but it's easier and more clear just to shorthand as a reference. This will give us mutable access to the position of the paddle as well as the player's settings. We can then query to see if the player is pressing up or down. Next, we're going to check to see if the player is pressing their input key and then move the paddle in the corresponding direction. This is done by using the input field, and we say input.press and then provide the settings move up key. This will query to whether the key that we've provided is currently being pressed. There are also variants such as just pressed and just released, used for if you want something to only happen once and not every frame that the key is being pressed. We will then take the position of the player, their translation, their Y translation, and then we will add, let's say 100 to it. Let's say 1 to it, because I've just done the math and 100 is going to be way too big. We can then repeat the same thing for if the player is pressing down. This, though, is going to subtract 1 from our movement. If we then come back up to the top and include our system, because this system needs to run every frame, we can't include it in the startup. Instead, we're going to add this system to a different schedule. This schedule is going to be update, which is called once per frame. We then pass in the move paddles function. And this should mean that when we press the corresponding keys, our paddles will move. Now, there is one issue that we have with this, and that's that we haven't actually controlled the paddles to be locked with relative to the frame rate. This means that pressing the keys will make the paddles move a different speed based on the frame rate that you have. In this case, very slowly. They're currently moving 1 frame per pixel. But if I was running at 30 FPS, they would be moving much slower. In order to correct for this, we're going to include another resource that Bevy's default plugins provides us, and that's time. The time resource allows us to get information such as the delta time, or the amount of time that's passed between frames. We can then use this multiplied by our movement speed. In this case, we're going to go movement speed 100 times time.delta, delta seconds. And the delta seconds is the number of seconds that have passed since the last frame, which means that this is now independent of the frame rate, allowing for a much more steady and stable control of the player, since lag and faster PCs will not have an advantage over slower ones. As you can see, there's very little difference between there and before, but that's simply because 100 divided by 60 is pretty close to 1. But as you can see, before, as I just did before, it is now possible for the paddles to go outside of the play area. In order to fix this, what we will do is we'll clamp the player's Y position so that it can't exceed beyond the top of the screen. The way we'll do this is whenever we update the player's position, we're going to say position.translation.y equals position.translation.y.clamp, and we're going to set the minimum to our 500, so in this case half that because 0 is the middle of the screen, so negative 250, and then we are going to add 75 to this. 75 represents half the height of our paddle. So if we were using variables to maintain the height of the paddle, we would need to set this to half the height of the paddle. Next, we will set the maximum value to 250 minus 75. So being the top of our screen minus half the width of our paddle again. We can then set this both times that we change the position. This should mean that it is no longer possible for the paddle to leave the play area. As you can see, the paddle can now no longer go off the play area. So now that we have our working paddles, next is to implement a ball into the game. So in order to be able to move the ball without necessarily moving our paddles as well, we need to make a component that just simply flags whether the ball is the entity that we are looking at. To do this, we will again make a component struct. In this case, if the ball is going to have a velocity, the velocity is going to be represented with a vec2. This will tell us which direction the ball is moving so that we can update its position. But like the paddles, simply running the game now won't do anything since we have not spawned the ball in. So now we are going to create an additional function called spawn ball. This is going to take in commands, and we're going to repeat a very similar process to when we spawned in our paddles. So much so I'm just going to copy paste it. But replacing the paddle with the ball and its starting velocity. In this case, the ball is going to be moving 100 units to the left and no units up or down. We are going to set the size of the ball to being, say, like 25 by 25, nice little square. This should make the ball relatively small, but still large enough to see. Next, like always, we need to include the spawn ball inside of our application. So we'll add that to our startup functions. Now when we're on our application, the ball is on the screen. Though as you'll notice, the ball is actually on the left side of the screen here. But that's simply because I didn't update its position relative to the paddle because I just copy pasted. If you set yours to 0, 0, it'll be in the middle of the screen. But the ball isn't moving. So what we need to do is update the ball's position each frame. We do this very similar to the paddle movement by creating a function called moveBall. We then query the ball's current position, as well as the ball's speed. We also, again, need time so that we can make the ball's speed independent of frame rate. So for each ball, we're going to update its position. The ball's position is going to be pos.translation plus equals ball.0 times by time.delta seconds. This will move the ball by its speed. This will cause each ball in the scene to be moved by its corresponding velocity. We need to extend our vec2 out to a vec3, since you can't add a vec2 to a vec3 in Bevy. We multiply by delta time to keep the speed of the ball stable even when there is frame lag. This should cause our ball to move in the direction we've specified when we run the game, after we include the system in our update set of systems. The ball is apparently behind the black, so we just need to make sure that our ball is on Z1. In order to prevent our ball from going behind the background, we need to make sure that our ball is on Z level 1. Since Bevy runs in parallel, we can't guarantee which system will run first, spawning the players and the background, or spawning the ball. So we need to make sure that the ball is on a different layout. Though as you can see, the ball just passes straight through the paddle, and that's because we're not doing any collision detection to determine whether the ball should bounce off the paddle or not. In order to do collision detection, we are going to make a new function called ballPlay. This one is going to take in a reference to all of our balls, as well as all of our paddles. The ball colliding function takes in a transform that is immutable, since we won't be moving the ball during collision detection, and a mutable reference to the ball itself so that we can update its velocity when it collides. We also need access to the paddle's positions, but we don't actually need to know anything else about the paddle. So we specify that with paddle so that we only get the paddle's transforms, but we need to specify without ball. Actually, it doesn't really matter. We need to specify with paddle so that we only get the paddles with the balls. We didn't need to do this previously since we were also requesting the paddle data, which implicitly restricts it to things with the paddle. Next, we need to loop through all of the balls and check if they are colliding with any of the paddles. So this is done by looping through all the balls and then looping through all of the paddles. We then do basic AABB collision detection to see if the ball has collided with In order to do the collision detection, we need to know some parameters, such as our ball width, our paddle width, and our paddle's height. This will allow us to check to see if our ball is within the paddle and make it bounce. In order to check collision, we use a basic AABB bounding box. This is done by taking the left side of the ball and making sure that its position is less than the right side of the paddle, and the bottom of the while the bottom of the ball is less than the top of the paddle. The top of the right side of the ball is less than the left side of the paddle, or is more than the left side of the paddle, and the top of the ball is less than the bottom of the paddle. Is greater than the bottom of the paddle. This is a simple way of checking to make sure that the ball is somewhere within, some part of the ball is somewhere within some part of the paddle. This is a basic collision check. We then multiply by -1 in order to flip the velocity. In order to add a little bit of variance and increase the challenge of the game, we're also going to add a random value to the ball's movement in order to make it less predictable in where it is going to go. To do this, we need to include the rand crate in order to allow us to generate random numbers. We'll just use a star because we don't care what version of the rand crate we import. All right, in order to give some variance, we're going to randomize the Y direction of the ball after it's been hit. This is done by importing the rand crate, thread RNG, which is just a random number generator, and then we call gen for an F32 and multiply by 100 to get to our speed factor. This does require us to use rand RNG in order to be able to call the gen function. This should give the ball a random Y direction every time it is hit by one of the paddles. If you were making a more useful game of Pong, or one that needed to be more fun, you could keep track on the player which direction they're currently moving and impart the movement direction of the player's speed onto the ball. This means that if the player is moving up, the ball will bounce off with more upward momentum than it otherwise would. This allows for somewhat player control of the ball, since they can move down to get in the way of the ball and then move up just as the ball hits them in order to deflect the ball in a different direction. This is beyond the scope of this video, but it would be an interesting thing to try and implement. Now, as you can see, the ball randomly picks a direction. The ball does now fly off the top of the screen though. This needs to be corrected by going into the ball's movement, and when we do a collision detection for the ball, we can also check to see if the ball's Y position plus half the ball width is greater than our 250 of our playfield. We want to flip the Y direction only. We do this by saying ball.0.y times equals -1. It's not what it's velocity. Velocity.0.y times -1. This will invert the Y direction when the ball hits the top of the screen. As you can see, the ball now bounces off of the edges of the screen. That's going to conclude this episode from Zero to Pong, since we have the bare minimum required in order to have a Pong game. There is still missing a whole bunch of things, such as scorekeeping and resetting the ball when it leaves the playfield behind the player. But those will be implemented in a future episode. In order to celebrate the release of this new series on Bevy, I've changed over from using Patreon to using Ko-Fi. You can find a link to my Ko-Fi in the description if you would like to support the channel and help these videos get made. I will also be enabling membership on YouTube in order to allow certain perks, such as having a special badge when I'm live streaming and you comment. The Ko-Fi will also have notifications and things enabled when I can work out how to do that kind of stuff. You don't have to support and don't feel pressure to support, but I would really appreciate any support you can give. You can also find in the description of this video a link to the vault files that contain the script for this video, as well as any other information that I've made about this series. It would also be much appreciated if you give this video a like and subscribe, since it really does motivate me to make more content. I will see you in the next episode, where we continue making our Pong game and adding more features, such as keeping score and making the ball respawn when leaving the field.